Welcome, fellow students, fellow scholars, intellects, wizards, archmages. Welcome. You and I are about to embark on a journey of epic proportion. You and I are going to be taking an Ivy League course on the subject of compilers from Cornell University. This journey will be difficult. You'll have a tale or two to tell when you come back. I cannot promise that you will come back, and if you do, you will not be the same. But don't be scared, we're going to take this one lesson at a time. So, this course is Cornell CS4120. I've heard that it's one of the best introductory compiler courses out there on the internet. As far as I know, it takes you through the construction of a compiler from the ground up, and by the end of the course, you'll have implemented your own compiler for a toy language, I think, that they give you. Personally, I'm doing this series to show you guys how I learn things and how I remember stuff, because I have a terrible memory, so I use a tool to help me. The tool is called Anki, and I'll be showing you how I use it. I wish I had it when I was actually doing my degree in 2017, because I would have done a hell of a lot better than I did. Anyway, the course consists of lecture notes, programming assignments, and supplemental readings from this book called The Dragon Book. If you don't know what that is, it is this book here, Compilers, Principles and Techniques and Tools. According to some, this is a legendary book among the industry, so I'm very happy to see the course referencing it because I've always wanted to read it. You see this knight here? This is us. This is us. And together, you and I are going to slay the dragon that is complex compiler design. So before we get started, one other thing, the course suggests to use Java as the language to build a compiler in, but personally I'm going to be using C++ just because I want to. The course recommends against it, but I'm honestly not scared. The best way to learn something, to jump in the deep end. Only real men use C++, so just got to give it a go. Anyway, thanks for watching, and I look forward to studying with you. Okay, let's get started. Lesson 1, Course Overview. Introduction. This is a course about the design and implementation of compilers. It is intended to provide a reasonably complete introduction to the major aspects of compilers, providing students with the mental toolbox to build compilers and to understand more advanced compiler techniques they may encounter later. Compilers are notoriously complex. Compiler construction was historically considered a significant challenge requiring major engineering effort. It is still not easy to build a compiler, but fortunately, techniques have been developed over the past few decades that greatly simplify compiler design. A running theme of this course is that the different parts of a compiler can be described in a declarative way. These declarative specifications can then be turned into efficient and clear code, even if we are programming in an imperative language. Okay, so straight up, what does declarative and imperative coding mean? What is imperative programming? Imperative program. Type of programming paradigm that describes how the program executes. Developers are more concerned with how to get an answer step by step. Okay. It comprises a sequence of command imperatives. In this, the order of execution is very important and uses both mutable and immutable data. Okay, so we're using mutable and immutable data, Fortran, C++, Yeah, okay. Declarative programming is, as the name suggests, is a type of programming paradigm that describes what programs to be executed. Developers are more concerned with the answer that is received, but how do you calculate things if you it declares what kind of results we want and leave programming language aside, focusing on simply figuring out how to produce them. In simple words, it mainly focuses on end result. It expresses the logic of computation. Haskell, yeah, Prolog is declarative. Okay, program specifies what is to be done. How do you actually... Example of declarative code. Declarative versus imperative code. Here we go. Show me examples. Procedural code. Okay, we're not going to make an account. Declarative program. What is declarative programming? When you write your code in such a way that it describes what you want to do, not how you want to do it. It is left up to the compiler to figure out the how. But the compiler can't possibly know every possible function. So you still have to figure out how to tell the compiler what you want. Just give me an example. Just show me an example. Here we go. Okay, imperative programming. Even numbers. Right, so, okay, so you step by step. Step by step tell it what to do. Declarative programming, you tell it what you want to happen. Yeah, okay, so declarative is more highly abstracted by the looks of it. Right, okay. Okay, so essentially the article is saying that compiler construction has become a lot more declarative, meaning you don't have to program as much. You know, there's a lot more abstractions, helpful abstractions that we can use, I'm guessing. A lot of functions that can do some good stuff for us. Okay. Compared to other introductions to compiler construction, this course focuses more on describing these specifications precisely, using inference rules and other mathematical techniques where other courses might be satisfied with less precision. The advantage of precision is that it gives us as developers, a well-defined implementation goal. Cool. So that it makes sense to talk about whether an implementation is correct or not. Awesome. These precise descriptions mean that we're taking a theory-oriented approach to compilers. In fact, a surprisingly large amount of computer science theory turns out to be useful for the design and implementation of compilers. Many theoretical contributions in computer science were originally motivated by compiler construction. That's pretty cool. That theory includes not only the theory of programming languages, but also the theory behind useful algorithms and data structures. This course is not just about theory, it's also intended to give students the ability to implement a real working compiler. Hell yeah, let's go. So we sometimes get into implementation details too. These details are often very interesting in their own right. Of course, what programming language you are compiling has a large influence on how you implement a compiler. Some language features require special techniques or impose restrictions on what compilers can do. Understanding how to build compilers naturally deepens our understanding of programming languages. Yes, that's what we're here for. And understanding the interactions between the language and the compiler also makes us better programmers, even when we are not implementing compilers. Cool. Challenge of compilation. A compiler is a translator from one language, the source language, to another, the target. Translation is not an easy task when the source and target languages are very different. In a classic compiler, the source language is a programming language designed to be understandable to humans, whereas the target language is assembly language or machine language, which is designed to be efficiently executed by hardware. However, other translations are useful and indeed commonly used. For example, the Java compiler compiles Java source code to Java virtual machine code, called bytecode. And the JVM runtime system has a second just-in-time compiler that translates frequently executed bytecode into machine code that the processor can execute directly. Okay. Alright. Seems one step too many, but hey, I don't know what I'm talking about. Do we need a compiler to run programs? No, programs can be run using an interpreter. For example, Java bytecode is executed by a JVM interpreter. Okay, yeah, so interpreter that simulates the execution of a hypothetical machine. However, software interpreters are much less efficient than processor hardware, so compiled code tends to execute at least an order of magnitude faster than interpreted code. In fact, a processor is simply a hardware implementation of an interpreter for machine code. Right, so I guess that's partially the reason why C++ and C run so much faster than Java, for example. The performance advantage of compiled code running on this hardware interpreter also means that compiled code consumes an order of magnitude less energy and generates an order of magnitude less heat. Of course, the actual step of compiling code can require a lot of computation. So if you're only going to run a program once, it's better to interpret it with a software interpreter. Okay. Yep. Compilation makes more sense for programs that are going to be run many times or for a long time. Okay, that makes sense. All right. I'm following. So, yeah, I was wondering why you would ever need an interpreter, but that makes sense. Source code and target code are typically quite different. Source code is optimized for humans to read and modify it. It tries to match human notations of language to some extent, and it has redundancy to help prevent programmer mistakes. Source code supports analysis and reasoning, either by humans or by algorithms. Target code, on the other hand, is usually optimized for efficient interpretation. It is compact, not very readable, and does not waste space on redundancy. Target code has often discarded much of the high-level structure of the source code, so it is hard to reason about. Even more important for compilers than the performance of generated code is its correctness. Debugging code is hard enough when you can trust the compiler. If the bugs might have been inserted by the compiler, debugging becomes truly difficult. The differences between the source and the target languages also make it more difficult to show that the compiler is doing its job correctly. Interestingly, it is actually possible to define with mathematical precision what it means for a compiler to be correct. So that's pretty cool. I had no idea that was a thing. It would seem like a compiler would have, I don't know, infinite possibilities of what kind of programs you can feed through it, so therefore it could never be 100% correct, but I guess we'll find out. When there is a defined semantics for both the source and target languages, that is a mathematical description of the behavior of both languages. So semantics is a mathematical description of the behavior of a language. I'm just going to double check that. What is semantics? Concern with meanings, logical semantics in compiler design. Semantic analysis is the task of ensuring that the declarations and statements of a program are semantically correct. Okay, that doesn't help. i.e., that their meaning is clear and consistent with the way in which control structures and data types are supposed to be used. Okay, right. So semantics is language correctness, essentially, right? And that's, yeah, that makes sense what they're saying. And indeed, a number of compilers have been developed along with proofs of correctness, even proofs that can be automatically checked to ensure they are constructed correctly. Awesome. Developing compilers with this high degree of assurance is not our goal here, but the approach we take of precisely specifying different parts of the compilation process is helpful for achieving this goal. Okay, so this word semantics is something that I'm probably going to forget the definition of. Super easy. So what I'm going to do is open up Anki, and if you haven't downloaded Anki, download from Anki Web. If you haven't downloaded Anki, I suggest you do it. Just trust me on this. Just watch how I use it. Your life will change forever. You'll never go back to not using Anki. Gonna wait for that to download. We're going to create a new deck for this course. And we're going to create another deck to go inside that deck. This will be 01 course overview, which was the name of the notes, I believe. So now we're just going to add a flashcard. Compilers. So this is the question that I'm going to be asking myself. What does semantics mean? And the answer is language correctness. I like to also give myself a little bit more information on the answers just to define it a little bit more. What do they say here? Interesting. Is it actually possible to define the mathematical precision, what it means for a compiler to be correct when there is a defined semantics for both the source, a mathematical description of the behavior of both languages? Yeah, that's pretty much enough for now, I think. Probably. Let's have a look. Meaning is clear and consistent in the way in which control structure and data types are supposed to be used. Yeah, language correctness according to some spec of the language. Like, yeah, it has to match it has to conform to the intent of the language. Okay, so now tomorrow we will get that flashcard and we're going to review that. So if you don't remember this, don't stress, because it's all going to come back to you eventually and you're never going to forget this in the future. Thank you, Anki. You'll see what I mean tomorrow in the next session. Okay. Here's an example of compilation. To see the flavor and the work that a compiler does, consider the following short function implemented in the source language we'll be using in this course. Its syntax is similar to a number of popular languages, so it should be easy to understand. So this is a function, takes an integer array, returns an integer. So I guess we have a variable for the length of the array, have a counter. AI equals plus 1. Okay. An unoptimizing compiler might translate the above code to x86-64 assembly code as shown below on the left. The variables from the course program are stored in memory on the program stack and are accessed using memory operands. For example, the variable A is stored at memory location RPB 16, where RBP is a register that points to the top of the current stack frame. Okay. Also notable is the control structure of the high-level source code, such as the while statement, has been replaced with low-level jump instructions like JNE and jump. Okay, so I know very little about assembly. I'm guessing it reads a little bit like basic. You essentially read it down and then you have jumps back up. So looks like we push something to this register. We move a variable into the register. I'm not 100%. I'm not sure at all. And then at some point, okay, it looks like these L1, L4, L5, L6 are the jump points. So at this point here, we jump to L7. At this point here, it looks like we're jumping to L4 in some alternate jump command. Looks like we're adding variables here. We're adding 1 to this RCX register and then comparing two registers by the looks of it, the value. I wonder what JNE stands for. It's probably like jump if not equal or something like that. Oh, I'll look that up later. I don't know assembly, so we'll get there. The unoptimized code is more efficient than the code an experienced assembly programmer could produce. But a good optimizing compiler can often match or improve on handwritten code, generating code like the code shown on the right. Variables are stored entirely in registers. The compiler has done a better job of choosing efficient instructions, and instructions associated with managing the stack have been removed because the stack is not used. I wonder where the stack RBP points to, okay, RBP points to the top of the stack. Minus 16, I guess we're going down to the stack at some point. Anyway, here we've got, yeah, obviously much more concise code. There's two jump instructions, JE and JNE. Seems like jump if not equal, jump if equal, not sure. Yeah, cool. There's a comparison, I'm guessing, and then this move function looks like it loads things into registers. Yeah, cool. The compiler usually doesn't finish the job of generating machine code. This step is left to the assembler. The result of assembling the optimized assembly code above is the following sequence of machine code bytes, expressed in hexadecimal, with their positions shown in hexadecimal in the left column and the corresponding assembly code shown on the right. Notice that the labels in the assembly code have been replaced by hexadecimal offsets. Yeah, okay. Obviously, like, impossible to read. But, yeah, pretty cool. Moving on. Anatomy of a compiler. It might seem almost magical that it is possible to translate source code to efficient, correct low-level code, and even more so that it can be done reasonably quickly. Yeah, that's true. It does seem that. The key insight that makes high-quality translation feasible is not to do it all at once. The way to solve a hard problem is often to break it into smaller, easier problems, and compilers are no exception. Instead of translating directly from the source code, a stream of bytes, to the target code, another stream of bytes, we define a sequence of compiler phases, each of which represents the original program differently. Essentially, in between the source and target languages, we define a sequence of intermediate languages that lie between the source and target and are designed for the convenience of the current compiler phase. To see how this works in a nutshell, let's look at our program statement like the following one might be represented in each compiler phase. If value is greater than or equal to 0, position equals value. Lexical analysis. The first step, okay, here we go. Now we're getting into it. The first step in compilation is to turn the input program, represented as a sequence of bytes or characters, into a tree data structure that supports later compiler phases. Lexical analysis divides up the input into a sequence of tokens or lexemes. These are the words of the program. Whitespace and other token separators are discarded. Yeah, cool. So yeah, you're grabbing every token. I guess this operator counts as a single token. Cool, okay. Syntactic analysis. The next step is parsing, which creates a tree structure that captures the syntax of the program, discarding syntactic elements such as parentheses that do not further affect the meaning of the program. The output of this phase is an abstract syntax tree. Okay. So it's control flow, then you've got a comparison, like a predicate here, and the children are the actual values, and the parent node is the operation. And I guess you work from left to right. In order traversal. I think it's in order traversal. So you start. No, that's not in order traversal. Let me just remember what in order traversal is. In order traversal 4, 2, 5, 1, 6, 3, 7. Pre-order is 1, 2, 4, 5, 3. So we're doing pre-order traversal in this case. Right. So pre-order is where you check the parent node first, then you go down the left tree, and then you recurse on the left-hand side, and then you recurse on the right-hand side. So 1, 2, 4, 5, 3, 6, 7. Yep. So we're doing pre-order traversal. Probably something that may be something to remember. So there's a bunch of terms being thrown around here, and when that happens, I like to add them to Anki. Anki's great for remembering things like this, like what is lexical analysis? Just a very basic summary. It's super easy to commit this stuff to memory with Anki. So I'm going to add this to Anki. Compilers. What is lexical analysis? It's the first step of compiling. It's where you it's where you convert the source program or the source files into essentially a stream or a list of tokens. Okay, next. What are lexemes? Lexemes are a basic lexical unit of a language consisting of one word or several words, the elements of which do not separately convey the meaning of the whole. So, an abstract is a basic abstract unit of meaning. Let's check Wikipedia. Lexeme computer science. Lexeme computer science. Lexical tokenization is a conversion of a text into semantically or syntactically meaningful lexical tokens belonging to categories. So lexical token is just like what we saw, just one word or symbol defined by a lexiprogram. Where is lexeme? Lexing can be divided into two stages: the scanning, which implements the input string into syntactic units called lexemes and categorizes these into token classes, and the evaluating, which converts lexemes into process values. I still don't 100% understand what a lexeme is. I guess it just says or lexemes. We'll just call it token or lexeme. So just assume they're the same thing. Cool. Syntactic analysis. What is syntactic analysis? The second phase of compiling. It's where you convert the token list, token stream list, whatever it is, into an abstract syntax tree. Yep, that's pretty good. That'll do. Okay. Okay, semantics. We learned about semantics before. It's essentially like the correctness of a language according to its like data structures, and it's, by the looks of it here, by its types, making sure the types are correct, I would assume. Semantic analysis completes the task of determining whether the source code represents a legal program. Yeah, so correctness checking. It often involves type checking. There we go. Additional information may be collected about the program during this phase, such as the types of program expressions. This information may be used to decorate the abstract syntax tree. Okay, yep, so the values we're comparing here are integers, and they resolve to a Boolean, and yeah, so this is an assignment operator, so an assignment operator won't have a type, I assume, but if it's an assignment operator, I'm guessing the left-hand side, the left child has to be the same type as the right child. I'm sure there's exceptions to that. Code generation. The compiler generates new representations of the program in multiple phases. Typically, there is an initial phase of code generation that produces an intermediate representation of the program. A later phase of the compiler generates target code. When the target language is assembly code, this phase is called instruction selection. Okay. A common intermediate representation is as a control flow graph. This would be an output of intermediate code generation. Just going to zoom in on that a bit more. if the value is greater than or equal to 0, do this, assign position to value. If not, if it's false, do something else. A later phase of code generation is instruction selection, in which the intermediate representation is translated to assembly instructions. Instructions can be generated as abstract assembly code. Abstract assembly code, okay, in which variables are assumed to be usable as if they were hardware registers. Okay. I'm just going to double check this, but a register, from my knowledge, is essentially a very small cache within the CPU. Hardware register. I just need to double check that. Hardware registers are circuits typically composed of flip-flops, often with many characteristics similar to memory, such as the ability to write multiple bits at a time using an address to select a particular register in a manner similar to a memory address. They're probably not exactly what I think they are, but they seem to behave that way. Special hardware-related functions beyond those of ordinary memory. Okay, so I'm guessing they can do, yeah, all those commands that we saw, the move, jump commands and stuff. I'm guessing that they can do cool stuff like that. Hardware registers are like memory with additional hardware-related functions, or memory circuits are like hardware registers that just store data. Oh, okay. All right. Yep, okay. Just double checking. So instructions can be generated as abstract assembly code in which variables are assumed to be usable as if they were hardware registers. Cool. For our example, the result of translating to abstract x86-64 assembly code might be the following. So we compare the value with 0, jump 1, L1, if it looks like if it's false, so JL, jump. I'm guessing this means if it's false, then jump to L1. But if it's true, obviously just move on to the next command, which is move value into the position variable. Cool. Look at that. We're learning assembly. Never thought I'd do that. Optimization. Optimization can be applied to make programs better. Typically, better means faster, although other goals are sometimes sought, such as reducing the memory footprint or the energy consumption of the program. Energy consumption. That's a crazy one. I don't see how energy consumption would differ much from like the speed, because like if you speed up the program and do less operations, less CPU clocks would be the same thing as less energy consumption. Anyway, optimization can be applied in almost every compiler phase. The most important optimization is register allocation, which assigns variables to hardware registers. Yep. Applying register allocation to the assembly code above might yield the following x86-64 assembly code. Okay, so we assign the value variable to this register, and we are also assigning the position to this RCX register, position variable to RCX register. Cool. Another optimization might allow us to use a more efficient instruction sequence that avoids branching. Compare the position, compare the value with 0. C move GE. So that's obviously some CPU instruction that negates the need to branch. That's pretty cool. So you don't have to do any jumping. Nice. I would look that up, but we may be getting too off topic at that. Like, I'll be sitting here learning assembly all night. Front end versus back end. The phases of a compiler are typically structured into a front end and a back end. Okay. The front end of a compiler comprises phases that do the first part of compilation: lexical, syntactic, and semantic analysis, intermediate code generation, and intermediate code optimization. So that's basically all the ones we've learned so far. These phases convert the program from input source code to an optimizable intermediate representation that is relatively free of details about the final target machine architecture. Okay, the front end is therefore largely machine independent and can be used for more than one target machine. Okay, so that's what they're talking about with this abstract assembly code that they were talking about here. So the assembly code you generate can run on, like, it's like quote unquote higher level assembly code that doesn't require specific architecture stuff. Like maybe this cmove GE command doesn't work on, for example, I don't know, it doesn't work on, I don't know, ARM processors or whatever. I'm just spitballing here. So the backend handles the machine-dependent aspects of compilation, instruction selection, and machine-dependent optimizations such as register allocation. Yeah, okay. So every architecture is going to be different. In principle, the backend is largely independent of the original source language. So if the intermediate code representation it takes as input is sufficiently general, the backend can be reused for multiple source languages. Yeah, cool. So yeah, like if our optimizer produces sufficiently general assembly language. It sounds crazy to say that. The bigger picture. The compiler usually only does one part of the task of producing executable code. After it produces assembly code for each of the compilation units, source files, an assembler is used to produce object code modules that have dependencies on each other. A linker resolves the dependencies between the object files and determines how to patch or extend the assembly code so that these dependencies are satisfied. A linker resolves the dependencies between the object files and determines how to patch or extend the assembly code so these dependencies are satisfied. Makes sense, I guess. A loader, often built into the operating system, then loads the linker output into memory and produces an executable image that the processor can interpret. A loader, often built into operating system, loads the linker output into memory. Yep, okay. Produces, yeah, makes sense. This is actually super similar to the this describes C++ perfectly. Like the G++, which is a C++ compiler, has all of these steps. Let me see. I'll probably do this later, but I can demonstrate how you can compile something. You can see, and then you can generate the assembly code, and then you can generate the object code, and you can look at all of those. You can use the object dump tool to go in and look at all this stuff. I'll probably demonstrate that later. Cool. Choosing an implementation language. Traditionally, many compilers were implemented using the language they were implementing. Huh, how does that work? This process is a bit like pulling yourself up by your own bootstraps. But these self-hosting compilers have some nice properties, such as avoiding dependencies on other languages and helping to identify limitations in the language design. That seems impossible, but I guess it's not. In the modern era, there are many programming languages available to implement a compiler in. and some of them may be better suited to writing a compiler than the language you are implementing in the compiler. So, self-hosting is less valuable than it once was. In practice, most modern general-purpose languages work reasonably well for compiler implementation. However, there are some trade-offs worth thinking about before you plunge into coding. A compiler is a big project with many moving parts, and one that is often too big for a single person to tackle alone or to complete in a timely fashion. That's why we're doing this together. Let's go. Good language support for modularity and separation of concerns is essential. A language with a static type system is also very helpful to guide design of interfaces and help constrain the interaction of different code modules. That's why we're using C++, baby. One pain point is that compilers use complex, often cyclic data structures that are shared across multiple compiler phases. A language with automatic garbage collection is recommended. Nope. We don't need that. We don't need that. C++, that's what real men use. These data structures can be compared across module boundaries without needing to complicate interfaces with memory management directives. Who's scared of memory management? Not me. Nobody here is scared of memory management. Performing unnecessary copying or worrying about memory corruption errors. I'm not worried about that. Are you worried about that? I sure as hell ain't worried. Languages that support pattern matching, particularly functional languages, work well for the more tree-structured front end of the compiler, but many of these languages make it more difficult to manage arbitrary graph structures, so they'll probably be less of a win for the back end of the compiler. So we're not doing this in Haskell. Okay, awesome. So that's the first lesson. I'm just gonna add some stuff here that I missed. So what have I got here? So yeah, one thing I want to remember is what is semantic analysis? So semantic analysis is determining the it's the third step in compiling, and it's essentially taking the abstract syntax tree and gathering type information and checking for syntax correctness, semantic correctness. So it takes the abstract syntax tree, gathers type information. Well, it does type checking. And checks the correctness of the program. Cool. Code generation. What is code generation? So it's it's the fourth step, and it's where you take the semantic tree, takes the semantic tree, and it checks. Sorry, it creates a control flow graph. So there may be many different phases of code generation. So there may be multiple types of this. Like later on doing instruction selection. So I'm just going to add that. I'm just going to add that here just as a little context. I don't expect myself to fully remember that, but just to help myself remember. There may be many different phases of code generation. Yeah. And intermediate representations of the program. So optimization obviously is optimizing the code, but maybe it might be good to remember a couple of these basic optimization methods. So you could say, what are some basic ways the compiler optimizes code? And the most important one is register allocation. Assigns variables to hardware registers, which I mean, it makes sense looking at it in the context of assembly. And you can also do things like using more efficient CPU instructions to eliminate the need for branching. Yeah, and the thing about Anki is if you're looking at this and thinking I'm never going to remember that, if in like 2 months' time this card hasn't helped you in any way, and it's every time you see it, it's just a pain in the ass to remember, and it's like it's not, and it just hasn't helped you at all, you can just delete it. Like these are all just it's like it's a living, breathing system where you work with it and it'll work with you. So don't stress out too much about these getting the perfect cards, because you can refine them as you go along. I don't need to remember this because I remember this already from learning about C++, learning about G++ specifically. So yeah, I'll probably have a little card for the front end versus back end, because I'll probably want to remember what that is. You know, and if this is like brain dead easy to remember, then I'll just delete the card later. So compilers, like what is meant by the front end of a compiler? And it's basically the machine independent phases, or the architecture independent phases. So yeah, lexing, semantics, syntax, optimizations. What else? Yeah, code generation, etc. So yeah, it's a more higher level or more generalized phase. What is meant by the back end of compiler? So these are the machine dependent phases. So the e.g. like optimizing for specific architectures. Optimizing, like even translating for specific, translating the intermediate representations into specific architecture. Yeah, that's it really. That's all that I care to remember at this point. So, awesome. That is lesson 1 done. Now, we have some readings to do. We got Dragon Book chapter 1 to 1.4. So, in the next video, we'll get into that.